Hello everyone, and welcome to the first video in this two-part video series on the ideal gas law. The ideal gas law is something that you can use to find a wide variety of different bits of information about a container of gas that you have. Now, one of the most important things you can learn about the ideal gas law is how to rearrange it to get the information that you need out of it. So the very first thing I'm going to do in this video is show you how to rearrange the ideal gas law to get 8 bits of information out of it. And then, because I know a lot of you are here on this video just to get that quick information, so I'm going to do that first. And then we'll go over a little bit more about the ideal gas law. And for the second video, I'll actually do some practice problems on the ideal gas law. Without any further ado, then let's go ahead and dive in. Now, for the ideal gas law, obviously we have PV equals nRT. Now, from this equation itself, you can get those 5 bits of information out of it. So you can solve for pressure, you can solve for volume, you can solve for number of moles, you can solve for the constant itself, which you usually don't have to use in this equation, and you can solve for the temperature. So first off, let's solve for pressure. First thing you do is you write out the ideal gas law, PV equals nRT. All you have to do to solve for pressure is divide both sides by the volume. Volume cancels out right here, and we're left with P equals nRT over V. And that's all you need to know for solving for pressure. So I'm going to go ahead and scoot this over. Next up, let's solve for volume. Again, you just write out the ideal gas law, PV equals nRT. To solve here, we just divide both sides by pressure. Pressure cancels out. We're left with V equals nRT over P. And that's it. That's how we solve for volume. So I'm going to go ahead and scoot the volume portion over here out of the way. There we go. There's solving for V. Next up, let's go ahead and solve for number of moles. So as with anything else, you just go ahead and write the ideal gas equation, PV equals nRT. What we're going to do here is we're going to divide both sides by RT, and that isolates N. So we're left with N equals PV over RT. There we go. That's solving for N. You'll notice these first few items, it's really just plug and chug. A lot of people, they go ahead and they memorize these equations, but if you understand how you get there, you don't have to commit any of this to memory. You really just solve it algebraically. So let's go ahead and solve for T. Actually, I'm going to go ahead and scoot down here. I'm going to put it right here. So once again, here is our gas law, PV equals nRT. To solve for T, we just divide both sides by nR. And that leaves us with T equals PV over nR. So I'm going to scoot this over. Now, this next one, you really probably won't ever find any need for using this, but just so that we have everything listed and handy, I'm going to go ahead and do it. Let's solve for the constant itself, PV equals nRT. I'm sure you have the pattern down by now. All we do is divide by what we don't want, and that leaves us with R equals PV over NT. So those are the first 5 bits of information that you can isolate from the ideal gas law. Here's where it gets interesting. We are going to talk about density. Now, I'm sure we all know density equals mass divided by volume. Now, here's the thing. If you look at the ideal gas law, PV equals nRT, there's no M. We have a volume, but we don't have mass. So how can we manipulate the ideal gas law in such a way that it has mass in it? Well, we know that we have number of moles, and number of moles is equal to the mass of the substance that you have divided by the molar mass of that substance. So if we were to just substitute m over mm into the ideal gas law, we would have PV equals, and I'm going to change this just for a little bit more clarity, grams over molar mass, and obviously grams is usually equal to our mass. So PV equals grams over molar mass times R times T. And to make this a little bit easier to work with, we could just rearrange this, not rearrange it, but we could just throw everything on top. GRT over molar mass. And you'll notice now we have things that we can work with. So let's take this one step at a time. Let's solve for our grams now, or our mass. So taking this new ideal gas law that we just put together, we could go PV equals GRT over molar mass. All we have to do here is multiply both sides of the equation by molar mass. And that gives us molar mass PV equals GRT. Now all we have to do is divide both sides by RT. And we've done it. Now we can say that the grams are equal to the molar mass PV over RT. That is how we can extract the molar mass out of the equation. So a lot of people say that this one's more difficult. If you understand the concepts, again, it doesn't have to be. Unless you want to, you don't have to commit all of these formulas to memory if you understand how to get there. So now let's solve for the molar mass. Let's use our new ideal gas law again. PV equals GRT over molar mass. So to isolate molar mass on one side, all we have to do is multiply both sides by molar mass. That's going to give us molar mass PV equals GRT. Now we just divide both sides by PV, and we've done it. We have molar mass is equal to GRT over PV. So now we've identified 7 out of the 8 bits of information that we can extract from the ideal gas law. The last bit of information that we need to extract is the density. Now, again, this one probably seems like the most complicated, but don't panic. We have all the bits of information that we need. So remember, density, as we discovered up here, is equal to the mass divided by the volume. Okay, is there anywhere that we have mass and volume in our ideal gas law? Of course there is. We have, let's see, what color should I use? I'll use green again. We have mass right here, and we have volume right here. So it just becomes a question of how do we work it so that both of those are on the same side of the equation? So PV equals GRT over MM. Okay. In order to isolate everything on the same side of the equation, let's go ahead and scoot molar mass over to this side like we've done many times before. So that will give us MMPV equals GRT. Next up, we want to isolate G on one side of the equation. So we do that, and we're left with G equals MMPV over RT. Okay, we're almost there. Now all we need to do is to divide by volume on both sides. And look at that. We've done it. G over V, which is equivalent to density, equals molar mass PV over RT. And I'm sorry, I should not have put the volume right there. It's simply molar mass times pressure divided by RT. So there it is. There is our density. So I'm going to go ahead and erase all of this. Scoot this up here. And of course, you can disregard that because we know that that's what density equals. So there you have it. There are the 8 bits of information that we can extract from the ideal gas law. Now, as I promised, I'm going to go ahead and go through a few of these items up here. We got that manipulation out of the way for those of you who are just on this video to find how to manipulate the ideal gas law. Now, to talk about the ideal gas law itself a little bit more, really the big things that we need to cover are these 4 items right here. All gas particles are in constant motion. Basically, that's what a gas is. When you have a gas, if it's going to behave in an ideal fashion, those gas particles, they're never standing still. And that's what a gas is, right? So that's an easy one to remember. It's not like a solid where it has a very uniform structure. It's a gas. Everything's in constant motion. Secondly, the particles are so small that their volume is negligible. Think about it like this. If you have this giant container and you have, actually, let's go like this. You have these tiny little dots. Can you see those dots? We have these tiny little dots inside this container, and all these tiny little dots are moving about in rapid motion. The volume of those dots really doesn't matter. They may have mass, but it really doesn't matter. So it's basically they're just zipping around, not interacting with each other. And that moves us into this third one. The particles don't interact. There's no attraction or repulsion. Another way to think of this is that the collisions are perfectly elastic. So again, it comes down to these dots are just so incredibly small compared to the volume of the container that they're in. When they collide with each other, there's no van der Waals forces, there's no hydrogen bonding, nothing. When they hit each other, they bounce off perfectly without attracting or repelling each other at all. And then lastly, and this is such an important one, average kinetic energy is proportional to the temperature and nothing else. When I took the DAT, they really drove this point home, and I've heard that it's on the MCAT as well, probably the PMAT, maybe the GMAT, I'm not sure there, but they're going to ask you things such as, okay, we have a container of helium gas and we have a container of argon gas. Which one has more kinetic energy at the same temperature? So you need to think about it like this. We have 2 containers. So here's another container, and let's just say these containers are the same size, and this one right here has helium gas, and this one right here has argon gas. And I'm going to make the dots a little bit bigger because remember, argon has a bigger size than helium. What it's asking is, if these 2 containers have the same temperature, let's just say 25 degrees Celsius, which one has more kinetic energy? Now, a lot of people, their knee-jerk reaction is to say, oh, the argon has more energy, because you think about velocity, mass affects the speed or the total collision force. And so a lot of people are going to be tricked by that question, and they're going to say that argon has more energy, but it doesn't. The only thing that matters is the temperature. So if helium and argon are at the same temperature, they both have the same average kinetic energy. The only thing that matters when it comes to energy is temperature. Now, what will change is the speed, because they have the same energy. Since argon is bigger, it's going to be moving more slowly. So if you had a container that had both helium and argon gas, and they were mixed and it was at the same temperature, you'd find that your helium was moving much faster than your argon. But when it comes to total overall energy, the only thing that matters is temperature. So that's it for this video. As I promised, I'm going to do another video where we work some actual practice problems. So I'll show you how to apply these manipulations of the formula. But thanks for watching, and we will see you next time.